Alright, here we are again, fourth week of the course, and well, as always, lots of stuff on the agenda, so let's get straight into it. So 4 things that I want to talk about in this video lecture. As always, I'll give a bit of a recap. Where are we now? What have we learned so far about regression analysis? And then we'll go into some new topics. Specifically, we'll talk about the F-test a little bit more. We already saw how to use the F-test in some situations, and now we'll take a look at other situations in which the F-test can be useful, specifically a situation where you want to test multiple parameters at the same time. So you want to do a so-called multi-parameter test. And then we'll go into a new topic where that will come in handy, being able to do multi-parameter tests, because we'll talk about how to model nonlinear relationships. So far we've assumed that our x variables and our y variable have a linear relationship. Now we're going to make the first steps towards modeling non-linearity, and then I'm going to close off with an introduction to bias and how bias might be related to the assumptions of the linear regression models. So that's what's on the agenda for today. So as always, we start with the recap. What do we know now? We now know that linear regression analysis allows us to estimate linear effects on some dependent variable in order to test hypotheses that generally will be formulated along the lines of the higher x is, the higher y is. So the more there is of x, the more there is of y, or the higher x is, the lower y is if there is a negative relationships. Yeah, so those are the kinds of hypotheses that we can test using regression analysis. And we saw that one reason why regression analysis is in fact absolutely awesome is because often these hypotheses will be based on a theory, and that theory usually will implicitly or explicitly make a causal argument. Because people have more income, they are more satisfied with democracy. Because countries have a higher level of education, they are more democratic. Often the theoretical stories behind such statements are causal stories. So if we want to test such theoretical hypothesis well, we want to get as close as possible to the actual causal effects, and that means that with the kind of data that we usually use, which is observational data, so it's not experimental data in the sense that we randomly assign a treatment to some observations and then put the other observations randomly into a control group and then compare the outcome, our dependent variable, before and after that treatment variable. So that would be a classical experimental design. Usually we can't do that. Yeah, we can't randomly assign 100 countries to be economically developed and then 100 countries to be not economically developed and then compare them before and after on a democracy score. It's not feasible. It's also not very ethical. So what we usually do in the political science is we're working with some kind of observational data, meaning simply the data that we were able to observe on certain variables for our cases, for instance, by doing a questionnaire survey or looking at some macro country level data that we can compile. Yeah, which means that if we want to make causal claims, then we have to worry a lot about potential confounders, so variables that might have an impact on both our dependent variable and on our independent variable, which may lead us, for instance, to find a relationship between x and y even though there is no relationship, because we did not take into account such a confounding variable. And so regression modeling allows us to control for such potential confounders as long as we can measure them, because if we can measure them and they are in our data, then we can also include them in our model as control variables, and then the estimates that we get for the variables that we do have hypotheses about will be a bit closer to the true causal effects that give rise to those relationships. So that's awesome. We also saw that technically we can, for instance, evaluate the goodness of fit of our regression models. So how well are the predictions, the predicted values of our regression model aligned with what we actually observe on our dependent variable. And we can do that with an f-test. And we also saw that you can use an f-test not just to compare the goodness of, to look at the goodness of fit of a model, but also to compare different models as long as the models are nested. So as long as there is a more complicated model and a more simple model, and you can get from the complicated model to the simple model simply by taking stuff out of the complicated model. Yeah, so this is, we already saw in the last video lecture that we can also use the f-test, an adapted version of the f-test, to compare any set of nested models in terms of goodness of fit. And we have seen that, well, besides the goodness of fit of the overall model, we usually also care, of course, about the individual coefficients in that model. And in order to evaluate the statistical significance of those individual coefficients, yeah, so can we reject the null hypothesis of no effect in the population, we can use the t-test. So this is where we are so far. So the goodness of fit of an entire model, f-test, statistical significance of an individual coefficient, t-test. So let's get a little bit deeper into that. So 2 weeks ago, I already started telling you that if you have an f-test in a simple linear regression model, then you can actually interpret the f-test that you get in your ANOVA table as testing two null hypotheses simultaneously. So that f-test that you get in your ANOVA table will test the null hypothesis that r square is 0. So in other words, that the explained variance of our model, if we would get that model based on the entire population, would be exactly 0, so that we explain exactly no variance at all in our dependent variable. But that we can use the same f-test to at the same time also test the null hypothesis that b1, that our regression coefficient in the simple linear regression model, yeah, so one where there is only one x variable included, that regression coefficient b1 is equal to 0 in the population. So in other words, that our x variable explains, doesn't have any kind of effect at all on our dependent variable if we would have been able to observe the entire population and then use that to get our regression model fitted. Yeah, so in a simple linear regression model, testing a null hypothesis that we can't explain any variation in our dependent variable is the same as testing that our x variable doesn't have an effect in the population. And well, you can see that that because both of these null hypotheses imply the same thing. They imply that our simple linear regression model, yeah, so yi equals b0 plus b1 xi plus an error term, does not fit our data significantly better than a model with no independent variables, so yi equals b0 plus an error term. In other words, it doesn't fit the data any better than just using the mean as a predicted value and not taking into account any other differences between our cases at all. Yeah, and these are nested models if you think about it, right? Because you can get from your simple linear regression model to the model where you're just using the mean as prediction by taking out the b1x term of your regression model. Yeah, so by taking out b1x, you get your very simple model of just using the mean to predict your outcome variable. Yeah, so yi equals b0 plus b1x I plus an error term. If you take out the b1x part, then you're just left with yi equals b0 plus an error term. In other words, the value on our dependent variable is equal to the mean plus the deviation score to that mean. So these are already nested models. And notice that if you think mathematically about what is happening here, is that what we're actually saying in our simple model, where we're just using the mean as a prediction. And basically what we're assuming in that case is that the regression coefficient for our x variable, so our b1 coefficient, is identical to 0. Because only if that regression coefficient is 0, then we would say, okay, that would mean that whatever value our cases score on our variable x is multiplied by 0. So if you multiply something by 0, the result is always 0. So only if the regression coefficient would be 0, we could say, well, in that case, then that is that entire B1xi part of the model is also identical to 0. So in other words, what we are doing with the simple model, if you're using statistical terminology, is we are restricting the coefficient to be 0. We are restricting our B1 coefficient to be 0. Yeah, restricting meaning that we force it to take one single value, the value 0 in this case. Yeah, so we're putting a restriction on the model by saying, well, if we would normally you would estimate a value for V1, so then in theory it could take any value, and the value it will take then is based on what does the data say. But if we take out the coefficient, that's the same thing as just assuming that it has to be 0, so it can only be 0. So we're restricting the coefficient in that case to be the value 0. And this is also the reason why sometimes when we talk about these nested models, again using the terminology from statistics, that often people refer to the simple model as a restricted model and the more complicated model as an unrestricted model, or sometimes it's also referred to as a full model. Because whenever you have nested models, remember what are nested models? If you have a complicated model and you have a more simple model, you can get from the complicated model to the simple model by taking stuff out of the complicated model. Well, taking stuff out is the same thing as saying these elements of our model have to be the value 0, because only if they have the value 0, we can leave them out of the model. So in other words, whenever you have nested models, this implies that you have an unrestricted model and a restricted model, where the restricted model is the simpler version of the unrestricted model. And it's restricted in the sense that it is setting things from our formula, from our regression model, to 0. So assuming that they can only take the value 0. Now, last week we already saw that it's not just about comparing a linear regression model to just using the mean as a predicted value, but that we can compare any set of two nested models and compare them using the f-test. And we saw that what we're then doing is we are testing the null hypothesis that r-squared change equals 0. In other words, that the more complicated, so the unrestricted model, doesn't add anything to the amount of explained variance compared to the more simple, so the restricted model, if we would have been able to calculate these models based on the entire population. So that by making the model more complicated, so in the situations that we saw adding more variables, we are not actually adding anything to the explained variance in the population. Yeah, so the null hypothesis that r-squared change is 0 in the population. So this is a null hypothesis where you can say, well, if I can reject that null hypothesis, so if my p-value is low enough to say, well, it's quite unlikely, given what we observe in our sample data, then you can say, well, the more complicated model, so the full model, significantly better fits the data than the restricted model, the more simple model. Now, again, that implies that we are restricting coefficients to be 0. So we have a complicated model and we have a more simple model, and the difference is one has more coefficients because we included more variables. Then the simpler model is basically a model where we are restricting those additional coefficients to be 0. Which means that you can also interpret this f-test as testing whether the additionally included x variables in your more complicated model are jointly significant. So taken together, are the additional variables that you included in your model, are they jointly significant? Yeah, so for instance, if we consider these two models, so we have the model where we say satisfaction with government for each person I that we're observing is equal to B0, the constant plus B1, the regression coefficient for income, so B1 multiplied by income plus an error term. And we also have a more complicated model where we say, well, it's not just about income, but it's also about age and happiness. So we have a full model in this case, satisfaction with government for each case I equals B0 plus B1 income plus B2 age plus B3 happiness plus an error term. Then if we would do an f-test comparing these two models in terms of goodness of fit, then that f-test, yes, would test the null hypothesis that r-squared change is here in the population. So that including differences in happiness and H does not explain any additional variation in satisfaction with government in the population compared to just using differences in income to explain differences in satisfaction with government. Yeah, so that R-squared change is 0 in the population. But at the same time, the same F-test also tests another null hypothesis, namely the null hypothesis that the regression coefficient we would estimate for H and the regression coefficient that we would estimate for happiness, both are the same value, and that value has to be 0. Yeah, again, we are restricting in the simple model, we are restricting the coefficient for H to be 0, and we are restricting the coefficient for happiness to be 0. So we are basically saying B2 can only take the value 0 and B3 can only take the value 0. Yeah, so an efficient way of writing that is, well, my null hypothesis states that B2 is identical to B3 and that is both are identical to 0. Yeah, so B1 is B3, B2 is B3 is 0. Yeah, so basically our F-test tests both of these null hypotheses because they imply the same thing. They imply that the more complicated model does not actually fit the data any better than the simpler model, right? So in this case, we refer to this null hypothesis test that we are doing as a multi-parameter test. Multi because, and we are now testing more than one parameter. And well, parameter, well, remember, our regression coefficients are estimates of the true population parameters, so the true population regression coefficients. Yeah, remember, inference is taking a sample estimate to say something about a population parameter. So in this case, because we are now testing more than one parameter, we're testing both the B2 and the B3 parameter, we are calling this a multi-parameter test. Okay, so this is a way to think about, well, comparing the using the F-test to compare model fits. What does that allow us to do? So it allows us to test the null hypothesis about R-squared change, but at the same time, that also implies that we are testing the joint significance of everything we took out of the model to go from the complicated model to the simple model. So all of the things that we restricted to be 0. Now, I'm going to go into a new topic, but the reason I wanted to cover this multi-parameter test first is because, of course, you're probably wondering by now, well, why the heck do I have to know this? What's the sense? We already have t-tests for the individual regression coefficients. We already have an overall f-test for the model of goodness of fit. Why would I want to do something like a multi-parameter test? And the nice thing is, well, there's lots of situations where actually theoretically that becomes something that's very interesting. And one of those situations is if we are dealing with certain types of nonlinear effects. So that's something I want to discuss now with you, modeling nonlinearity. Because you might think by now, okay, we know how linear regression analysis works, we know how to include multiple X variables in our models, we know how to interpret them, but you might also think, yeah, but isn't it more complicated? The world isn't just linear, right? So the good news is, yeah, that's absolutely correct. The better news is, and yes, we can use that. We can actually do something with these non-linear effects. As a matter of fact, we can keep using our linear regression model and still analyze non-linear effects with that linear regression model, which may appear a bit confusing, but I'll show you how you can go about doing that, because you might care about nonlinear effects. So for instance, you might stumble upon some theory that you want to test, which argues that there is a so-called inverted U-shaped relationship between economic development and the level of democracy in countries. Yeah, inverted U-shape, literally meaning the shape of that relationship is the letter U upside down. Yeah, so in other words, what you're expecting then is that, or what you're arguing then is that If economic development increases, then the level of democracy first increases, but somewhere there is a peak, and at some point, if the level of economic development even further increases, then the level of democracy decreases again. And there are actually variations of theories that you might have heard about in the democratization course that make exactly this argument. So of course, we would like to, well, test those theories, because again, that's just a theory. Yeah, cool story, bro. Does it actually work like that in practice? So we can think about how can we use statistical models to do that. Well, it means that we can now think about, okay, what exactly does our theoretical hypothesis now say? Well, it says at low levels of economic development, we're basically expecting higher economic development to lead to more democracy. But at high levels of economic development, we are expecting that further, even higher economic development actually leads to less democracy. Yeah, so we are translating this argument of an inverted U-shape into a theoretical hypothesis for which we say, well, if this theory is correct, then this is what we should be seeing in the data. We should be seeing this effect of economic development that's non-linear, where we say if we look at the level of democracy against the level of economic development, then first democracy goes up. But at some point we kind of get this peak, and then if we even go further in economic development, then democracy goes down again. So the cool thing is we can actually test this hypothesis, which implies a nonlinear effect with a linear regression model. So how does that work? Well, it works by including something in our model that is sometimes referred to as a polynomial. So we can include so-called polynomials in our regression model to model non-linear effects. So for instance, if we take a look at our example, what would we need to do in terms of regression models? Well, if we would say, well, we have data on different countries, so each I is a case, a country, on the level of democracy, measured in some way that is theoretically valid and reliable, and some measurement of economic development, and let's say we're using GDP, gross domestic product, to measure economic development, then we could now estimate a regression model where we would say, well, we have a constant B0, we have a B1 regression coefficient for our GDP variable, but now we also have a second coefficient for our GDP variable, but not the original GDP variable, but GDP squared, so GDP taken to the power of 2. And then include whatever else we want to include in our model in terms of control variables or other variables that we have hypothesis about. Yeah, so what we have here is we have included a polynomial for the GDP variable. So basically, you could say we have what we would have done if we would have actually wanted to estimate this model. Let's assume a level of democracy and GDP are already variables in that data set. Then we would have created a new variable, GDP squared, where we've just, for the values for that new variable, we would just have taken the values of GDP to the power of 2. So GDP times GDP for each country that we observe. So then we have a new variable, GDP squared, in our data set, and we include that as another X variable in our model. So that means that we now have modeled a curvilinear relationship by including this polynomial for GDP. Yeah, a curved relationship because, as you might remember from high school, taking something to the power of 2 in a linear function results in a parabola. Yeah, in this curvilinear relationship. Yeah, so by including GDP squared, we are modeling now a curvilinear relationship with GDP. So this can be generalized to any kind of variable for which we want to see whether there is this curvilinear effect. So if you have a hypothesis that says, well, there might be a curvilinear effect between whatever dependent variable you have and whatever independent variable you have, then for that independent variable you can include that variable again, but then taking the squares of that variable. Yeah, so the general shape for a curvilinear effect is then our dependent variable I for each case I is equal to a B0 constant plus a regression coefficient B1 xi, so just the regression coefficient for the original variable, plus a regression coefficient B2 times x to the power of 2 for each case I, so that x variable squared, again plus an error term, and of course you can include whatever else you want in that model, but that's the basic idea of a curvilinear relationship in a regression model. And we can make it even more complicated. So we could even say, well, maybe we expect a cubic effect. Yeah, cube meaning taking something to the power of 3, which if you want to visually think about, well, what would that look like? Think of the letter S, a letter S that fell over. So rotate your letter S by 90 degrees, and that's what a cubic effect looks like. So up, down, and up again. So we could even do that, but then we would just say, well, for that x variable that we want to say, well, that might have a cubic effect. So we're going to include the original variable, x. We are going to include x to the power of 2, and we're going to include x to the power of 3. Yeah, so that same x variable is then in our model 3 times the original variable, the variable squared, and the variable cubed. So taken to the power of 2 and taken to the power of 3. And by doing that, we can even model these cubic effects. Yeah. And we could go even further because we could just add higher order polynomials to our model if we think there is an even more complicated relationship with even more complex curves that go up and down in different ways. So we could extend that to include any number of higher order terms. So we could say, well, we are going to add b4 times x to the power of 4. And if that's not enough, we could even say, well, we're going to include b5 x to the power of 5. Yeah, so we could include more and more of these higher order terms to have ever more complicated relationships between our independent variables and our dependent variable. And notice that the basic model is still exactly the same. So we still have our dependent variable equals something b0 plus b1x plus an error term. So the overall model is still a linear model. There is nothing inherently nonlinear about it. The only thing that we did is we included transformations of our x variables. So taking these polynomial transformations of our x variables. Yeah, so that means that we have a great deal of flexibility with regression models to capture effects that don't that aren't just the more of x, the more of y, but that might be much more complicated and much more complex. Yeah, so that's what we can. That's one way we can go about modeling nonlinearity. Of course, that we can do this raises the question: should we do this? And I would say I would be very, very careful as to how far you should go in including these nonlinear effects and how complicated you make these models. For one thing, I would be hard-pressed to think of theories that we typically use in the social sciences. Yeah, so political science is a social science, of course. There aren't that many theories in our field, I think, that can really say, that can really lead to predictions that are much more complicated than a curvilinear effect. So it is not uncommon to have theories where a curvilinear effect is predicted, but theories where something like cubic effect or even more complicated effects are predicted. That's really, really rare. To the point that I think that those are almost non-existent. And of course, if you don't theoretically expect such a complicated effect to exist, then why would you include it in your model? Yeah, so I would say if you want to use these polynomial terms, so modeling this nonlinearity, do that if you really have a strong theoretical expectation about their existing according to the theory, this nonlinear effect. So that's what would be one situation where I would say, well, okay, if my theory really predicts a curvilinear effect, yes, of course, include x to the power of 2. One other situation where you might consider including nonlinear effects is if you have very strong indications that just taking a linear effect is a very bad representation of the effect of your x variable. And what do I mean by that? Well, think about situations where you don't necessarily have a theory that predicts a nonlinear effect for this x variable. It might even just be a control variable that you're using, but you have very strong indications that it's not a linear effect. So for instance, if you have a large data set, so you have lots and lots of observations, and you are analyzing the residuals, which is something that we are going to discuss and see a little bit more as to how to do that in this video lecture, and then in the B lecture, and with some other material this week. So when you're expecting these residuals, you might see that there is a clear nonlinear pattern present in your residuals. So that there is an obvious, for instance, U-shaped pattern going on in your residuals. That might be an indication that there is this kind of nonlinear effect, even if you have no theoretical expectations. And if you have very strong indications that is indeed the case, and it's not just a couple of observations, so it's really a strong pattern across lots of observations, then you might consider including such a nonlinear effect for one of your x's. Yeah, but I would say do that if you have strong indications. Don't just do that because you want to mess about, but be really careful with being a bit careful with not making the models more complicated than they need to be. And the reason for that is because there is always a trade-off as to how complicated we can make these models, which we discussed already in one of the previous lectures a little bit, this problem of overfitting. Overfitting meaning that we are making the models too complicated for the amount of data that we have. So at some point, because nobody is stopping us, of course, we always have the risk that our models are just so complicated that the amount of data we have is insufficient to allow us to reliably estimate our models. And this is really a situation where you could say, well, at some point you run the risk of basically modeling the noise instead of the signal you're getting from your data. So basically picking up on the idiosyncrasies of your sample data set, and then you might have a super complicated model that you fitted to your sample data, but that model would not at all work well in the population because you're basically just picking up on all the noise that you get in that specific sample. Yeah, so overfitting, that's a real issue, especially if you're working with smaller data sets. You have to be careful about that. So regression models don't become better by just making them more and more complicated. You have to be very careful about, okay, what is it that I need? How much data do I have? So how complicated can I reasonably make it? Yeah, so this is something that you should always be aware of, that just making them more complicated for the sake of making them more complicated will not work very well. So you have to be a bit careful with that. Yeah, so try to avoid overfitting. So that's as a general outline as to how to go about modeling nonlinearity, if at all. Now a bit more practical. When you do that, so when you include polynomials in your model, do make sure that you always include all the lower order terms in your model. What do I mean by that? Well, let's look at an example. Let's say you're expecting a curvilinear effect. Don't do this. Don't estimate a model where you're including your x variable squared and nothing else. No, include the original x variable, so the untransformed x variable, and the x variable that is squared. So include both of those in your model. Yeah, so that is what I mean with lower order terms. Yeah, so the lower order terms in this case is the x is the lower order term and x to the power of 2 is the higher order term in this model. Yeah, so whenever you include higher order terms, make sure that you also always include all the lower order terms as well, because otherwise you will get horribly misleading results. And if you're unsure about why that is, well, of course, ask me maybe on the Zoom meeting on Friday. But I've also prepared a Excel sheet where you can mess about with polynomial effects. And also a bonus assignment where I make you do that. And maybe then you yourself will already start to understand what it would mean to not include the original x variable in the model, what we're then basically restricting and what that means for our relationship. Yeah, but until you've played around with that, I would say, well, just for now, understand that you should never do that, because it will give you very misleading results. So of course, also, for instance, if you say, well, I have a cubic effect that I want to test from x variables, don't just include the cubic effect. No, include all the lower order terms as well. So your original x variable, x to the power of 2 and x to the power of 3. Yeah. So that's really important that if you do this, include these higher order terms, then also include also all the lower order terms, or your results will be super misleading. Yeah. So that's a general rule that for the kind of data you would be working with, is probably always a good idea. It's never a good idea with the type of data that we typically work with to not also include the lower order terms in the regression model. Now, going back to our example of saying, well, we expect a curvilinear relationship between GDP and the level of democracy. Yeah, of course, we can then say, well, we estimate this regression model, and then we get a coefficient for GDP, and we get a coefficient for GDP squared. And of course, we could look at the t-tests for those coefficients. But then, of course, the question is, okay, so now you have one hypothesis about an effect, but you have two coefficients. Which one do you look at? Well, if you look at the coefficient for B2, which you might want to do because you say, well, that's the thing that makes it a nonlinear model, do notice that the only thing that this additional coefficient really tells us, yeah, the p-value that's associated with that, is whether the curvilinear relationship fits better than just a linear relationship. And that's basically the only thing it tells us. It doesn't tell us about the overall effect of GDP, because we need both coefficients to represent the effect of GDP. So the only thing that the t-test for B2 tells us is actually, does the curvilinear relationship fit better with our data than just the linear relationship? But that's not what our hypothesis says. It doesn't say, well, curvilinear fits better than linear. It actually says, no, there is an effect, and that the effect itself is non-linear. That's a curvilinear relationship. So to represent that, we just saw, well, we need all the terms. So we need B1 and B2 to represent the effect that we expect on the hypothesis here. Yeah, that's so at low levels of economic development, higher economic development leads to more democracy. But at higher levels of economic development, higher economic development leads to less democracy. We need both B1 and B2 to estimate that relationship. So what do we need to do? Well, yes, look at the t-test for B2. But also test whether GDP and GDP square are jointly significant, because you need both to represent the relationship. So in other words, you want to also test the null hypothesis that B1 and B2 are both 0 in the population, which we just saw we can use an f-test for, because what we are doing here is we want to test multiple parameters at the same time. So we can do a multi-parameter test. We can do an f-test where we're testing the null hypothesis that our regression coefficient for GDP and the regression coefficient for GDP squared are both 0 in the population, right? So in general, I would say if you're doing nonlinear effects with polynomials, first check the t-tests for the higher order terms. So in this case, it was the coefficient for GDP squared, to test whether it even makes sense to consider a curvilinear effect or a higher order effect on your dependent variable. So first look at, in our example, the coefficient for GDP squared, whether that's associated with a p-value that's low enough that you are willing to reject the null hypothesis that that regression coefficient is 0, because that's the same as saying, well, if I can reject that null hypothesis, then at least it makes sense to even consider a curvilinear or more complicated effect on our dependent variable. But then also use the f-test to test the joint significance of all the terms that you need to represent the effects. Yeah, so use that f-test to test whether your x variable has overall the expected nonlinear effect on your dependent variable. And what I would also recommend, because most people have a hard time when they see these nonlinear relationships in terms of coefficients to understand exactly what the curve looks like. Yeah, so that's often quite hard if you're not really into mathematics. One trick that I can tell you if you want to know whether the curvilinear effect, so if you have if you're having just a curvilinear effect, so taking something to the power of 2, whether that's a U-shaped or an inverted U-shape. So is it a parabola where it's going up and then down again, or a parabola where it's going down and then up again? One trick to remember that by is if you think about the value of the coefficient for that higher order term, for that x to the power of 2 term, then if it's a positive coefficient, well, positive people tend to smile, and when they smile, the corners of their mouths go up. So that's a nice way to remember that if you have a positive coefficient for that higher order term, that indicates that the parabola is like a smiley face, basically. So going down and going and then up again if you go from left to right on the x-axis. Whereas negative people frown a lot, so the tips of their mouth tends to go down. So if you have a negative coefficient for that term, you can think about a parabola where it's going up and then down again. Yeah, so the other way around. So that's a nice trick to remember that, but even then still it's very, very hard to visualize. Yeah, okay, but exactly what is the location of that curve relative to the x and the y axis? People find it quite hard to interpret that. One way to, circumvent the issue is, look at the predicted values of your dependent variable once you estimated the model, visualize them in a graph. For instance, a scatter plot of the predicted values across the x-axis of the independent variable, the x variable, and then see, is the shape of that relationship, is that actually what I theoretically predicted? Or does it look completely different to what I theoretically predicted? Yeah, so that's a trick to get yourself to understand what that nonlinear effect actually looks like if you have a hard time figuring that out based on just the estimated coefficients. Yeah, because the shape of the curve is itself determined by the coefficient for instance, the x to the power of 2 variable. But the location of that curve is dependent on, in this case, all the lower order terms, which is why we need to include them. So your coefficient for the original x variable determines also where the location of that curve is, as does the constant of b0. Yeah, so again, don't panic if you don't know how to exactly to interpret them, but just plot the predicted values in the graph, and then you can just look at the fancy picture of your nonlinear effect. Yeah, so let's say you expect some kind of curvilinear effect. Well, then, okay, start with estimating the regression model where you include that curvilinear effect. Yeah, so include your x variable to the power of 2 and whatever else needs to be in the model as control variables, for instance. Then the first thing I would do after you estimate that model is check the significance of your B2 coefficient. So in other words, doesn't even make sense to consider a nonlinear effect. Does a nonlinear effect fit better than just a linear effect? And then once that is the case, when you can say, well, yes, so if it's statistically significant and the coefficient is describing a parabola of the shape that you expect in terms of is it going up, down, or down, up, yeah, then you can use the f-test to compare the model with x and x square included to a model where you're taking both of those out. Yeah, so the a model where you don't have x or x squared included as x variables in your model, and you can use an f-test to compare those models because they are nested models. The models without x and x squared is a restricted version of the model with x and x squared included. And then you can say, well, if that f-test is also statistically significant, then you find support for your hypothesis, but do make sure that the curve that you have estimated is also actually in line with what you theoretically expect. Yeah, so take a look at the predicted values before you draw your final conclusion. Yeah, so that's really important because, again, if you're not used to interpreting these polynomials, then visualizing the effect just in your head might be quite hard. So then always make sure that you check the predicted values across the range of your independent variable and see whether that's actually in line with what you theoretically expect. So that's it for curvilinear effects. Of course, you will get to practice in the assignment because, I can imagine that some of these things might be a bit daunting the first time you see them and not everything makes sense yet, and that's completely fine. As always, don't panic, get to work on the assignment and come to the lab sessions, ask for help, or come to the Zoom meeting on Friday afternoon, ask for clarification. Yeah, we're here for you as always. Okay, so that's about modeling and nonlinearity, and also showing you a nice example of where it actually makes sense to have these more elaborate f-tests where you can compare the goodness of fit of any set of nested models. Now I want to introduce a somewhat new topic, and I'm just going to make a relatively short introduction to that because it is basically, it goes really to the heart of what exactly are we doing with these linear regression models, and exactly what are we assuming with these linear regression models, and what happens if our assumptions turn out to be wrong about our regression models. One of the consequences of that can be that we're going to have a problem with bias. So I'm going to make a first step on of introducing this complexity to you. Yeah, of course, because we want you to be able to not just estimate regression models and have nice statistically significant findings, but we want you to be able to critically use such regression models and be able to criticize others when they are using such models, and that involves knowing exactly what assumptions we are making with these models and what happens if these assumptions aren't true, and especially how that might impact on bias. So, of course, then let's start with the most important question probably. What is bias? Well, bias has now, of course, a everyday language meaning, many of those actually. But in statistics, it has a very specific meaning. So when we talk about bias in statistics in general, we talk about a situation where there are systematic differences between our estimates and the actual population parameters to which they refer. Yeah, remember, we are doing inferential statistics, so we are estimating, in this case, regression coefficients, but we actually want to say something about the underlying population parameters, so the actual population regression parameters, which we can't actually observe. So bias is a situation where we say that there are systematic differences. Yeah, so of course in each individual sample we don't expect our estimate to be exactly identical to the population parameters. We know that they are not, and that's not a problem at all. As a matter of fact, most of statistical theories is exactly about describing how that relationship between individual samples and the population parameters actually works, and how these individual estimates are distributed. Remember, that's what the sampling distribution tells us. So that's not a problem. What is a problem is if there are systematic differences between our estimates and our population parameters. So what do I mean with systematic? Well, again, remember, we know that our estimates will be different than the population parameters in a single sample. And this is just because we know, well, it's just a sample. We don't have all the observations from the population. So we know that there is going to be an amount of variation in our sample estimates around the true population parameters. Yeah, so our regression coefficients might be higher than the true population parameter, or they might be lower than the true population parameter in any specific sample. And to what degree they vary around that population parameter, well, that's what the sampling distribution describes. And that's not an issue. What is an issue is that think about this always in the context of, okay, what would happen if I would take a new sample and replicate my analysis from the same population, and then again I take a new sample and replicate my analysis. So in other words, as always, think about, well, what would happen in the long run with my estimates, with my regression estimates in this case, or whatever other statistical estimates you are taking. What would happen in the long run if I would take all potential samples from a given population and each time do my statistical analysis? What would happen to the individual estimates? And what you want is a situation where the average of all those estimates is identical to the population parameter. Remember this from the central limit theorem when we talked about the means. We say, well, the expected value of sample means is identical to the population mean, and the same is true for regression coefficients. The central limit theorem tells us that the expected value of our regression coefficients is identical to the true population regression coefficient. Yeah, so there shouldn't be any systematic difference between the two. So if we would take the average of all our regression coefficients, that average should be identical to the population regression parameter. And that's true for every statistic. Yeah. So in other words, bias is a situation where this is not true, where something is going wrong in such a way that the average of our sample estimates is not identical to the true population parameters. Yeah, so that's bias in general. What is bias specifically when we talk about regression analysis as a subset of statistical analysis? Well, what do we do in regression analysis? We estimate coefficients and we estimate standard errors. Yeah, because those are the two most important things that we care about, right? We care about the effects of our individual variables that we find in our sample, but ultimately we care about what can we say about the population, and for that we need to know how much uncertainty there is associated with these sample coefficients. In other words, we need the standard errors. So if you think about regression models, the two most important things are always the coefficients and the standard errors. And if we get those right, then everything else will be okay as well, because everything else is basically derived from that. Yeah. So bias in regression analysis means that we have a systematic difference between our coefficients and or our standard errors and the true population coefficients and standard errors that we try to say something about. Yeah, so think about, for instance, a situation where if you would repeat the analysis that you just did on every possible sample that you could take from a given population, and you would take the average of all those sample coefficients that you would find, that average turns out to be higher than the true population regression coefficient, or lower than the true population coefficient. That's a situation where you say, well, okay, here we have a situation where there is bias. And the same for the standard errors. Yeah, think about you estimated your regression model on one specific sample, and you think about, okay, what would happen if I would do this for every potential sample from a population? Each time I'm going to calculate a standard error. Then again, your standard errors might be biased if the average of all those standard errors isn't identical to the population standard error, for instance, because they are on average actually higher or are actually lower. Yeah, so bias in regression analysis basically means that the average of your all potential regression coefficients and or the average of all potential standard errors are not identical to the true population coefficients and standard errors. So there are a couple of different reasons why you might have bias in your regression analysis. And one of those is that if you estimate linear regression models, you are actually making some assumptions about your data. And 4 of those assumptions are the assumption of additivity and linearity, the assumption of independent errors, the assumption of homoscedasticity, and the assumption of normally distributed errors. Yeah, so those are 4 standard assumptions that these models make, which may or may not be true again, because they are assumptions. Yeah, assumptions meaning we assume them to be true, but they might not be true. Yeah, and if they are not true, then our regression analysis will be biased. Yeah, so the average of our coefficients and or standard errors will not be identical to the true population regression coefficients and standard errors. Yeah. So those are the 4, let's say, classical assumptions. Later, I'm going to make an introduction of 2 of those for now, because that's enough for this lecture and that's enough for the assignment so far. Later we'll talk about the other ones, and we'll also talk about some other issues that can lead to bias, where it's a little bit more dependent on the specific situation we are talking about, whether or not we can consider this bias and whether or not it's problematic. And those would be the situation where you have outliers, the situation where we are suffering from what you call endogeneity bias, which, for instance, one case of that is the so-called omitted variable bias, where we are leaving variables out of the model that should be in the model, and the situation of selection bias, where our sample is not really a random selection from the population, and so there's some kind of systematic difference between our sample and the population, and so some kind of selectivity in the sample. Yeah, and that might lead to selection bias. So I'm not going to go over all of these just yet. We're going to do this step by step, but I'm going to make a start with talking about some of these. So, and I'm going to start with really the classical assumptions, additivity, linearity, independent errors, and then probably in one of the next lectures, we're going to talk about homoscedasticity and normally distributed errors and the other things like outliers and endogeneity and selection bias. So let's start with additivity and linearity. So if we're estimating these linear regression models, yeah, yi equals b0 plus b1 x1i plus b2 x2i plus whatever else we put into the model plus some error term. Well, one thing that we assume to be true is that our effects are additive and linear, because that's exactly what the formula says. Notice that the formula has all these plus thingies, yeah, b0 plus b1 x1i plus b2 x2i, which means that, as you by now know, that if we want to calculate the predicted values, we can just add up all the individual components here. So b1 multiplied by the value of x1 for a specific case plus b2 multiplied by the value of x2 for a specific case. Yeah, we can just add them all up to get the right predicted value. So that's the assumption of additivity, and related to that is the assumption of linearity, because we just have an equals sign there. There's nothing otherwise mathematically fancy going on. So that indicates that our y variable linearly depends on whatever we put on the right hand side of that equals sign, that it actually makes sense to model our effects as linear effects. Yeah. So additivity is the idea that the combined effects of the different x's in our model can be obtained by adding up the individual effects of each x variable. And linearity implies that, well, our regression model is basically representing the effects as straight lines. Yeah, x's are linearly related to our y's, then this should also in fact be true of the effects. So later in the course we will see situations where we have violations of both additivity and linearity. But for now you can already think about, well, let's assume, going back to our example of GDP and GDP squared, let's assume that the true relationship between GDP and the level of democracy in countries is in fact a curvilinear effect. But we did not include that in our model, we just included it as a linear model. Then we have a situation of bias, because the true effect is in fact not linear, but we treated it as linear because we didn't include the polynomial for GDP in our model. So in this case you would have a situation where we would be violating this assumption of linearity, and that would mean that our estimates for the GDP effect are biased. They are not on average identical to the true population effects that we want to say something about. So that's the assumption of additivity and linearity. A second assumption that we are making with these models is that the errors in our model, yeah, so the error term that we add in our model, yeah, again, for each observation, that's the difference between what we predict and what we actually observe on our dependent variable, that these errors are independent from each other. So in other words, if you think about these regression models, again, I'm bringing back this picture that you saw a couple of times already. The idea is that we are fitting a regression line. Yeah, that's what our model describes based on our individual data points. So all these little black dots indicate individual data points. And there will be a difference between what we predict, yeah, so that's the regression line, and what we actually observe, so the individual data points. And that difference are those red lines, which, if we talk about the sample, we call them residuals. If we talk about the population, we call them errors. And of course, errors, the true population errors, is something that we cannot actually observe, but residuals is something that we can observe. Well, one assumption that we need to make about the actual errors in the population is that they are independent from each other. So in other words, the value of these red lines, so how far removed individual cases from the regression line are, there should be no correlation between between all the cases. So on average, there should be no systematic relationship between the cases as to how far removed they are from the regression prediction, how far removed they are from the regression line. And probably it's very hard for you to think about, well, why would that ever be the case? Luckily, we can just talk about concrete situations where that can be the case, and hopefully it will also clarify a little bit about why that is the case. And there are typically in political science, there are two types of situations where you might have an issue with this assumption of independent errors. And one is that your data set might not be a simple random sample like the one we are using until now. Yeah, simple random sample meaning that we have a population, and from that population, every case in that population has the same probability of being included in the sample, and there's otherwise no systematic relationship between the probability of being included in the sample between the cases. Yeah, so one situation where that tends not to be the case if you observe the same cases over time. So let's say that we would be analyzing a data set where we have the level of democracy measured for the Netherlands from 1945 until 2020. And we have yearly observations for the Netherlands. So we have the level of democracy. And let's say we also have the level of economic development. And you might say, well, great, we have all the individual observations. Yeah, Netherlands in 1945, Netherlands in 1946, Netherlands in 1947, and so on, until we have Netherlands in 2020. Why not just estimate a regression model so we can see, well, what was the effect of economic development on democratic development in the Netherlands? The issue with that is that these are not different cases. It's always the same case that we are observing. So we call this, in general, a longitudinal data set. So when we have cases that we observe multiple times. More specifically in this case, because we are following one case over time, we would call that a time series data set, because we have a series of time observations for one unit of analysis. So those are situations that you will face quite a lot in political science, that we have a unit of analysis or multiple units of analysis that we are following over time, so for which we have multiple observations. That is often going to imply that whatever you find on your dependent variable in each specific time period is going to be somewhat related to previous time periods. Yeah, going back to the example of democracy in the Netherlands, probably the level of democracy in 1947 is going to be a little bit like the level of democracy in 1946, and much less probably like the level of democracy in 2020. Yeah, the level of democracy in 1998 might be quite alike the level of democracy in 1997, and maybe also a little bit alike the level of democracy in 1996. So values on your dependent variable that are close together in time, for instance, will be somewhat similar. Yeah, that's often going to be the case, that you will see that basically you would be able to some extent to already predict the next observation in time just knowing the current observation. Yeah, that there's an element of predictability over time because, changes can be slow, or it might be the case that whenever something is high in one period, then it's always, or on average, always low in the next period. So there might be an element of predictability in your dependent variable. Well, and of course, your dependent variable, the value of that is also going to be related to the value of the error term, yeah, because that is, of course, the difference between what you predict and what you actually observe. So in other words, what you will get then is an element of predictability in your error term. You will to some extent be able to predict the error in one period based on a previous period. Yeah, and this situation where you have this predictability over time, this is called autocorrelation. Yeah, autocorrelation is the idea that over time we are able to predict the values of our errors. This is also sometimes referred to as serial correlation. And sometimes autocorrelation is also used in different contexts. I'm going to not try to completely overburden you with all those nuances already. But just for now, let's see, autocorrelation or serial correlation is this idea that because we have the same unit of analysis or the same cases that we observe multiple times, that there is going to probably be some element of predictability in our error term, that we can predict the error for today by the error that we observed yesterday or last year. Yeah, this is the problem of autocorrelation, which means that our errors are not independent. So that's one that you will see quite a lot in the political science field. Another one that you will see a lot is a situation where you have multiple cross-sections. So for instance, samples from various countries. As a matter of fact, the European Social Survey that we are working with for the assignments, well, we only use data for the Netherlands in the assignments, but there is data for all other for lots of other European countries as well, included in the European Social Survey. So you could say that's actually the European Social Survey. If we would use the entire data set, then you could say, well, that's actually a two-stage sample that we are using, because basically you can think of it as first having selected a selection of countries from the population of countries, and then within each country, the European Social Survey drew a random sample from within that country. Yeah, it's not like they just said, well, this is the population of Europe in its entirety, and we are just going to give everybody in Europe, based on the entire European population, the same probability of being included, and then we're going to start sampling. No, they first selected countries, and within those countries, they selected people. Yeah, so this is really a two-stage sample. Yeah, and this is sometimes referred to as multi-level data, because there is really two levels in our data set. If you think about how the sample came about, there is a level of individual persons from different countries, but at a higher level there are different countries that were already selected, from which we selected these individual persons. And again here, if you think about this, you would often see that, well, people that live in the same country tend to be a bit alike. So for instance, this satisfaction with democracy variable that we are analyzing in the assignments, it's not unlikely that people from the same country will exhibit some degree of similarity in how satisfied they are with democracy. Yeah, so for instance, the Netherlands, people from the Netherlands might be somewhat similar in their level of satisfaction with democracy. Not all the same, but some degree of similarity. Yeah, as a matter of fact, it might be the case, for instance, that let's say in the Netherlands, on average, we are quite satisfied with democracy. Maybe there are other countries where on average people are not at all satisfied with the level of democracy. Yeah, so if that's the case, and quite likely that is the case, you will see that, well, just knowing that somebody is from the Netherlands already to some extent allows us to predict the value on a dependent variable, because we know, well, even though the specific person might have a high or low value, we know that on average the level of satisfaction of democracy in the Netherlands is quite high. So there's a pretty good chance that this person will have a relatively high value on satisfaction of democracy. And maybe there's another country and we know, well, the average level of satisfaction of democracy is really low in this country. Then for each individual person, to some extent, we can already predict the value on satisfaction of democracy. Again, not perfectly, but we know on average these persons from this country will tend to have a lower value on satisfaction of democracy. So there might be some degree of similarity within these cross-sections, within countries in this case. And this degree of similarity is often referred to as the intra-class correlation. Yeah, again, it's a bit like autocorrelation. Autocorrelation is basically over time. Interclass is within a class of observations, and class is class in the general sense of the word, some higher level to which we can order the individual observations, in our example, countries. Yeah. So that's the situation of intra-class correlation, where you can say, well, we can already to some extent predict the value on the individual cases, not perfectly, but to some extent we can predict the value on the individual cases by just knowing to which higher order unit they belong to, by knowing to which country, for instance, they belong to. So whenever you have those situations, we are talking about some intra-class correlation, some degree of likeness within cross-sections, which is also, by the way, the reason we are not using the entire European Social Survey, but just one country, so we don't have an issue with intra-class correlation. Yeah, and again, if you can to some extent predict your dependent variable, that implies you can also to some extent predict the error. Again, because what is the error? It's the difference between predicted and observed values. So if there's a degree of similarity within the observed values, there will be a degree of similarity in the errors as well. So in other words, both of these situations, when you have autocorrelation or when you have intra-class correlation, is likely to lead to a violation of the assumption of independent errors. Yeah, it's likely then that if you have autocorrelation or if you have intra-class correlation, that your errors are not going to be completely independent from each other. So there's going to be some systematic correlation in your error term across the individual observations. So what happens if that is the case? Well, and you just estimate your linear regression models. Well, there are basically two consequences that can result from violating this assumption of independent errors. And one is that your coefficients themselves might be biased. That's not always the case, and I'm not going to delve too much into the complexities about when it is and when it isn't, because that's something for the next methods course to really delve into. Of course, do ask me if you're curious in the Zoom sessions. But for now, for you, it's enough to know that you might have a situation, if your independent error assumption is violated, you might have a situation that your coefficients are biased, so that they're on average wrong. Isn't always the case. Sometimes they're completely fine. So they could be okay, but they might be biased. However, what is almost always going to be the case if your errors are not independent from each other, and basically the moment you get any kind of autocorrelation or interclass correlation, what is going to happen is that your standard errors will be biased. As a matter of fact, they are even biased in a predictable direction. They will be downward biased, meaning that the values you get for your standard errors will on average be too small, will be smaller than the true standard errors that you want to estimate. Yeah. So independent error assumption violated means that your standard errors will be downward biased. So the values that you get for your standard errors will be too small. Now stop, pause and think. What would be the consequence of that? What would be the consequence of having standard errors that are too small? Yes, some of you hopefully figured this out by yourselves already. If your standard errors are too small, that means that you are going to have a larger risk of finding a significant effect when there really isn't one. Yeah, so rejecting your null hypothesis when in fact you shouldn't be rejecting your null hypothesis because there really isn't an effect. As you might remember from your previous statistics courses, when we incorrectly reject a null hypothesis, so when we say there is a significant effect, well, there actually isn't one, that means that we are making a type 1 error. Yeah, and of course, we always run the risk of making a type 1 error. Yeah, we know that because we don't have the entire population. We only have just a sample. But at least we want to know what that risk is. So if we're saying we're working with an alpha level of 0.05, that's identical to saying that we are willing to take a 5% chance of incorrectly rejecting a null hypothesis. Or in other words, if we were to take 100 samples and redo our analysis, we are willing to accidentally say that there is an effect while there really isn't one in 5 out of those 100 samples. Yes, so downwardly biased standard errors means that we will be too quick to call something statistically significant while it's actually not. So that the p-values that we get, because what are the p-values based on? Coefficient divided by standard error gives you the t-value. T-value is compared to t-distribution to give you the p-value. So if your standard errors are too small, that means that the number you're dividing your coefficient by to get a t-value is too small, which means that the result of that, the t-value will be too large. And if the t-value is too large, that means that we are further out in the t-distribution than we are supposed to be. We are further out in the tail of the t-distribution than we are supposed to be. In other words, our p-value will be lower than it actually is. Yeah, so the true probability value is actually larger than the one that we are getting because our standard errors are biased downward. Yeah, so that's of course something you want to avoid. Now, just one thing, if you're using the previous edition of the field book, which is completely fine, there isn't that much difference between the two versions. One of the things that thankfully got fixed is the 2013 version of the field book suggested to use the Durbin-Watson test to test for a violation of the independent error assumption. That's you can, but that only works with time series data, not with cross-sectional data. So you can use that for situations where you have one unit of analysis that you follow over time, and then it will give you some information about the degree of autocorrelation in your data, but it doesn't work, for instance, for data like the European Social Survey, where we have basically multi-level data of people nested in different countries, because those are not observations that are ordered by time, and the Durbin-Watson test is really based on having observations that are ordered over time, so that test doesn't work. So watch out if you are using the old edition. Don't use the Durbin-Watson test for cross-sectional data. It makes no sense to use it in that context.